In this video, we will talk about average cost. So let's begin by defining what it is. So average cost. So the average cost is equal to the total cost divided by the number of items. And notationally, this is written as, so the average cost is written as C for cost, and then we put this line on top of it, and that means average cost. And then I write of X equals, so total cost is C of X, and the number of items, the variable for the number of items is X. All right, so I'm going to box this. This is our definition of average cost, and we have this way of notating it by writing C with a line on top of it. That will indicate that we're talking about average cost and not just total cost. So let's do an example. We looked at this example in the last video, but I want to do a related question. So blue books sell for 85 cents a copy. The cost of X copies to the student store is C of X equals 20 plus 0.05x plus 0.002x squared dollars. So we did parts A through D of this example in the last video. So I just want to continue the example and do some more parts to it. So part E of this example is, what is the average cost of 200 blue books? So in other words, with our notation, we write C with a line on top of it of 200. That means the average cost of 200 blue books. And using the formula for average cost, we take the total cost, which is C of 200, and we divide it by the number of items. In this case, it's 200 items. All right, so if we plug 200 into our cost function, we get 20 plus 0.05 times 200 plus 0.002 times 200 squared, and then divided by 200. And if we simplify this, if we evaluate what this is, it comes out to, and the units are dollars, so $0.55, or in cents, we could write that as 55 cents. So the average cost of 200 blue books would be 55 cents each. Okay, so this would be our average cost. $0.55 each, or 55 cents each. So next, let's figure out when our average cost is increasing and when it's decreasing. So this is part F. It's a multiple choice question. It's asking average cost is, so is it always increasing, always decreasing, and so on and so on. We have these answer choices, and we need to figure out which is correct about average cost. So to answer this, we're going to need to figure out when the average cost is increasing and when it's decreasing. And we showed how to determine when a function is increasing or decreasing in the last video. So we are going to use our method from the last video to find when a function is increasing / decreasing, so when it is increasing and when it is decreasing. And we did that using the derivative. Okay, so the function that we care about here is average cost. We are trying to say, when is average cost increasing? When is average cost decreasing? So we are going to need to write down a formula for average cost. So C bar of X is equal to our cost function on top divided by X. And our total cost function is 20 plus 0.05x plus 0.002x squared. That was our cost function. And we divide that by X. All right, so we have a function. We have our function. And now let's use our method to figure out when is this thing increasing and when is it decreasing using the derivative. So the first step, remember, was to find where the derivative of this is equal to 0 or when that derivative is undefined. Okay, so to take the derivative of this, we have a fraction, something divided by something. And we don't have a rule for taking the derivative of a sort of a fractional function like this. And because of that, we need to find a way to simplify this. So it becomes a function that we know how to take the derivative of. So we need to simplify before we can take the derivative. So we need to simplify our function into a form that we actually know how to take the derivative of. All right, so our function, the average cost function, we can take this fraction and we can split it up into pieces. This is 20 over x plus 0.05x over x plus 0.002x squared over x. And as a check, that's the same thing as what we had above, because when you add fractions together, when their denominators are the same, you just get to add the numerators together. And that gives us the average cost function that we had up above. All right, so now let's continue to simplify. If I want to take the derivative of something like 20 over x, it's helpful to rewrite it as 20 and then bring the x up to the top as x to the negative 1. With the next term, the x's cancel and I get 0.05. With the next term, I can also cancel an x and be left with 0.002x. All right, so that's my average cost function. At this point, it's simplified enough to where we can take the derivative. So let's take the derivative. So we are ready to take the derivative. Remember, d dx, that's just a notation for the derivative. And when I do, we get average costs derivative, so c bar prime of x equals. So for 20x to the negative 1, the negative 1 comes to the front, and I'll get negative 20. And then x to the, I subtract 1 from the power, and that makes the power negative 2. The derivative of 0.05, because it's a constant, is 0. And the derivative of 0.002x is 0.002. Okay, so if that was a little bit unclear or a little bit fast, I definitely encourage you to pause the video and really think through that on your own. Make sure you see why this bottom line is the derivative of the line above it. Okay, so now that we have the derivative, we need to set that derivative equal to 0. Okay, we're going to need to set it equal to 0 and then also figure out when it's undefined. So when we set this equal to 0, we get negative 20. Let's bring the x to the negative 2 to the denominator. Then it becomes x squared. And then plus 0.002 equal to 0. So if we rearrange this, we will get 0.002 equals 20 over x squared. Okay, and now if I rearrange this, I can move the x squared to the left. And I can divide by 0.002. So the 0.002 will come to the bottom of my fraction. And we get 20 divided by 0.002. And this is something we could simplify. We have 20 divided by 0.002. Let's write that as a fraction. That is 2 over 1,000. And when you divide a number like 20 by a fraction, when you divide anything by a fraction, you multiply by the reciprocal. So we'll get 20 times 1,000 over 2. So with the 20 and the 2, I can divide each of those by 2, and be left with a 1 down here, a 10 up here. So 10 times 1,000 is 10,000. So if x squared equals 10,000, and square rooting both sides, we get x equals plus or minus 100. All right, so we get x equals plus or minus 100. But one of these values doesn't make sense. So x cannot be a negative number because it's a quantity here. X is a quantity. So it can't be negative. All right. So as a result of that, we just look at the value x equals 100. Okay, so that was one part to this step. one part of this step was we needed to figure out when the derivative equals 0. But we also need to figure out when the derivative is undefined. So let's think about that. Let's think about when the derivative is undefined. So I'm going to do that in a column to the side, because this is where I started thinking about when is the derivative 0. Now let's find when the derivative of my average cost function is undefined. Okay, so the only type of thing that can make this derivative be undefined is because I have a fraction here, when the denominator of that fraction is 0. And so the thing that would make this happen is if the denominator equals 0, and the denominator was x squared, and that's 0, so x squared equals 0 when x equals 0. Okay, so 0 is the value that makes this derivative undefined. So that's our first step. We take the derivative, figure out when it equals 0, and that was at 100, and we take the derivative and figure out when it's undefined, and that was at 0. Then steps 2 and 3 are related. That involves making a sign chart of the derivative and then plugging test points into the derivative. And maybe let me say here, from each subinterval. So let's review how we do this. So we make a number line. And we put the numbers that we got in step 1 on the number line. So we got 0 as one of our values, and we got 100 as one of our values. But also at 0, because our variable here is a quantity, x is a quantity. So it can't be negative. And because x can't be negative, we're not going to worry about anything to the left of 0. So I'm going to put just a bracket like this at 0, because x cannot be a negative number. All right, so now I pick a test point in each subinterval. So I have a subinterval. I don't need to worry about the interval to the left of 0, because x can't be negative. But I do need to worry about the interval between 0 and 100. So I could plug in any number I wanted to in that interval. But I'd like to pick something that makes the algebra nice. So maybe I'll pick 1. That seems like a simple thing to plug into my function. And then for something bigger than 100, so remember, I'm going to have to plug in to my derivative function. That was negative 20 over x squared plus 0.002. Okay, so ideally I'd like to plug in some nice number. Okay, so and I think 200 is going to be a little bit easier computationally than doing something like 101. But if we wanted to do 101 or 102 or 1,000 or a million even, all of those would work because all of those are in this subinterval. All right, so now let's start to make our sign chart. Okay, so what we do is we make a row for the derivative and we make a row for the original function. And then I put a line at each of these values that's on the number line. And I make rows for this sign chart. And what I need to do now is plug in these test points into the derivative. So remember, the derivative of average cost was negative 20 over x squared plus 0.002. So let's plug in our test points. So if we take this derivative and plug in 1, we get negative 20 plus 0.002. And that is a negative number. So when I plug in 1 into the derivative, we get a negative number. What about if I plug in the other test point? What about if I plug in 200? If we plug in 200, we'll get negative 20 over 200 squared plus 0.002. All right, so I've worked this out ahead of time using the calculator, and this ends up giving me 0.0015, which is a positive number. So plugging in 200, my derivative is positive. So when the derivative function is positive, the original function is increasing. So my function here would be increasing on this interval. So that means the graph would be sort of rising. And when the derivative is negative, like it was on this first subinterval, the original function is decreasing. It is going down. On a conceptual level, the reason why that is when the derivative is positive, that means the slope of the tangent line on this interval is positive. And if our tangent lines have a positive slope, that means our function is rising, it's increasing. All right, so we know the intervals where it's decreasing and the intervals where it's increasing. We just need to write them down. So our average cost function was decreasing on the interval from 0 to 100, and it was increasing on the interval from 100 to 100 to infinity. Whoops, not to 0, to infinity. Okay, so that's where it was increasing and where it was decreasing. So I wrote this little reminder to myself. We need to answer what the question was asking. And here was the original question. What does average cost do in terms of increasing and decreasing? And now we know that it's decreasing initially, but then it switches to increasing. And that is answer choice 4. It's decreasing initially, then it switches to increasing. And that's our answer. In terms of our goals for this section now, we have done goal 4. We've defined the average cost function and done an example to get comfortable with how we compute the average cost, and then also how do we determine where it's increasing or decreasing using our method with the derivative involving sign charts. So in the next video, we will do a conceptual example.